Welcome to today's vector lesson on geometric operations. Some of the prior knowledge that you may need for this lesson are vector representation and negative vectors. Okay, we're going to first talk about vector addition, and what better way than to start with an example. So we got Robo who walks from home for 200 meters east 30 degrees towards north, and it goes to the library, and then it turns and it goes 400 meters west 45 degrees towards north to the school. And we want to determine Robo's school location relative to home, and that's basically the total displacement, which can be calculated by the addition of these two vectors. We will start off by drawing a coordinate system labeling the east and the north direction, and Robo starts right at the origin. The direction that the Robo is traveling is from east 30 degrees towards north, so we draw that angle and then we draw the magnitude of 200 meters. This will mark our position A, which is the library. Now we draw another coordinate system, and this time Robo travels west 45 degrees towards north, so we draw the angle, and the magnitude of our vector is now 400 meters, so it's approximately 2 times the previous magnitude, which was 200, and we will label that, and the new position is position B, which is the school. Now we want to determine Robo's school location relative to home, so from home we will connect a vector to the school, and that will be the total displacement, or simply vector A plus vector B. This vector shows where Robo started and where it ended, and the distance of this, or the magnitude of this vector, is the shortest distance from the starting position to the final position. So whenever we want to add two vectors, in this case A and B, we're going to draw the first vector first, and then at the head of the first vector we're going to draw vector B as shown in the diagram, and then we're going to join the tail of the first vector to the head of the second vector. And we can do this for many vectors. We can also do it for 3 vectors. We will continue drawing all of the vectors, and then finally we will connect the tail of the first vector to the head of the last vector. Now, subtracting vectors is not that difficult. All you have to do to subtract a vector is to add the negative. So for example, if you're subtracting vector B from A, you can rewrite that as vector A plus the negative of vector B. A zero vector is a vector which has a length of 0, and to represent it you need to make sure you write a 0 with an arrow on top indicating that it is a vector. In this example, we got vector A, which is a vector in the direction right. If we do A minus A, it's same as A plus negative A. So we'll take vector A and we'll add the negative of A to it. And you can see the resulting length will have a 0 length, and therefore it's a 0 vector. Note that if you had any vector, let's say vector A, and if you added a 0 vector to it, you will still get the same vector because there's no length being added to it. And if you start from the beginning of the original vector, which is vector initial, the tail of vector A, and if you go to the head of the final vector, which is still the head of vector A, you will still get vector A as a final result. Let's talk about a scalar multiplication. If we have k, which is a scalar value, meaning that it has no direction, it only has a size or a magnitude, then if you were to multiply that value by a vector, let's say in this case vector A, you would get a vector in the same direction of A if k is larger than 0. So here we got vector A, and if I was to multiply it by 5 over 4, then I will get a vector in the same direction, but something that's 5 over 4 times vector A, and 1 over 2 will just be half of its size, but it'll be in the same direction. If you multiplied k by a vector A, and k was a negative value, then it will result in a vector that is in the opposite direction. So looking at the diagram, negative 1 over 2a will have half the size of a, but it's going in the opposite direction. Finally, if you multiplied k by vector A, and if k had a value of 0, then it will result on a 0 vector, meaning that it will have no length, and a vector with no length is a 0 vector. Now I'm going to fast forward through the summary of this lesson. You can write any notes if you want. Basically, the big takeaways is how to add, subtract, or multiply vectors. Now let's look at a couple of examples. For the first example, we're going to use this square to determine the following vectors in terms of vector a and b, which are indicated in the diagram. So we're going to look at vector OM, MN, and MP. Feel free to pause the video to try the question out first. For the first example, we want to get vector OM. So we start at O and we're going to try to see how we can get to M. We first have to travel to L, which is vector A, and then we got to go from L to M, which is vector B. So OM is simply the addition of vector A plus vector B. For part B of the question, the vector originates at M and terminates at N. And if you notice, it's exactly the opposite to vector A. And for two vectors to be equal, they need to have the same magnitude and the same direction. So the vector negative A has the same magnitude and the same direction as vector MN, and therefore it is equivalent. We can also write this as negative A plus B minus B if you want to write it in terms of both A and B, but negative A is often acceptable. Now, part C is a little bit more challenging. We got a vector that originates at M and terminates at P, and that's halfway of vector MO because those two diagonals actually bisect. And we know that the negative of vector MO is OM, so this is equivalent to half vector OM. And we already know what vector OM is in terms of A and B, so we can write this as half vector A plus vector B in brackets, or we can use a distributive property and get half of A plus half of vector B. To check our answers, we can start with a vector that originates at point M and move halfway towards the negative direction of B, and then halfway towards the direction of negative A, and we can see that we end up at point P, which is vector MP. Now for our second example, we're going to show geometrically that if we were to add the size of vector A to size of vector B, it would always be bigger or equal to the size of vector A plus B. Now to do this, we are going to actually draw it out. We're going to draw vector A to the right, and we're going to draw a random vector B, and we are going to draw a circle which indicates the magnitude of vector B, and we are going to draw many vector B's, and then we are going to connect the tail of vector A to the head of vector B to see the resulting vector, or the addition of vector A and B. And we can see that we're forming triangles, and in these triangles, the addition of A plus B is the hypotenuse, and A and B are the shorter sides of the triangle. And in order for us to have a hypotenuse which is equal to the size of the smaller sides, then the angle between vector A and B has to be 0. I know in the video I have said it's 180, but if the vectors are in the same direction, then the hypotenuse will be the same length as the size of vector A plus the size of vector B. And that's the only case that is possible for a triangle. In all other situations, the hypotenuse will always be smaller. I will leave you with one practice question. Try it out, and at some point I will try to make a video with full solutions to it. I hope that this video helped you get an idea about how to geometrically add, subtract, and multiply different vectors. Have a great day.